Okay, so chapter 13 is our last test, but today we're not really going to do a confidence interval or a test. We'll do those Monday, Tuesday. Today is kind of like, okay, so chapter 13 relates all the way back to chapter 5. So when you get after your quiz, you're going to get a review worksheet that's from chapter 5. Do you guys remember linear regression? So like y hat equals a plus bx. We predict that for every whatever, this increases by what. You guys did in algebra 2 too? Sum of the squares, sum of the square residual. All that stuff's going to come back. I know. So 13.1 is really kind of a review from chapter 5. And then 13.2 is more the test. This very rarely shows up on the AP test, this whole chapter. I mean, it does in chapter 5, kind of, but it's been a while since they've had the test that we do in chapter 13 on the AP exam. Not saying it doesn't show up, it's just rare. So anyway, in chapter 5, we studied linear regression, and we did y hat equals a plus bx. Now, that was based on a sample and sampling variability and may be incorrect. It can be used to estimate the true regression line, which is y hat equals alpha plus beta x. Now here's what's also confusing. This alpha and beta are not the alpha and beta we've been working with. It's not like type 1 error, type 2 error. It's just the Greek letters they use for A and B, for slope and y-intercept. So it can get kind of confusing. So the y hat value has two interpretations. One that you've seen before. This is usually what we do. Y hat is usually the point prediction of an individual y value at x equals some x star. So usually this is what we write. So I'm trying to make it not. This is what we wrote in chapter 5. We predict a student at PSEP will get an ACT score of 25. So we usually use the word predict whenever we're trying to, it's whatever. It's not a high score, but not a low score. Okay, there's another one that's not a point prediction, that y hat can be a point estimate. Can be a point estimate of the mean y value when x equals some x star, some specified value. So we could also say the average ACT score for students at PSEP is a 25. So we either write it as a point prediction, which is kind of what we did in chapter 5. Chapter 13 is saying it can also be a point estimate for the mean y value. So everything we do in chapter 13 has to do with slope and equations of lines. So if you look at alpha plus beta x, there's going to be some error. So this fancy E stands for error. The actual y value for any particular x is based on two terms. The mean y value at that particular x and a random deviation. So y equals y hat plus some error. I'm just going to go through this. You don't really need to know all of this, just so you know. If the error term was not included, that would imply that all points fall exactly on the true regression line. So one of our assumptions of the regression model is that the error has a normal distribution with a mean of 0 and a standard deviation of sigma sub e, so S sub e. So basically what happens, here's your nice little diagram. If we're looking at linear regression, and I had all of us go out and find a sample, we would all get slightly different lines. So we would all get, like, there's the true, this would be the true regression line. But we would all get slightly different lines, right, due to sampling variability. So what we kind of end up doing is we create a normal distribution at each x value. So if I put together all 33 of our lines, we would get a normal distribution at each x value. So it would have some sort of sigma. So then we can use this to predict as long as we're at one specified x value. So like if I'm looking at height and weight, if we all went out and got different samples of height and weight of, I don't know, a certain, like seniors at PSEP, we would all have slightly different lines. But we could say, okay, at the height of 5 feet, here's where all of our weights are. Okay, so we're going to do inference for regression. But really we're going to look at that Monday, Tuesday, for in 13.2. Okay, today is kind of just a review. So flip to the next page. So like I said, beta is different in this chapter. Beta is just the population regression line. It's the average change in y associated with 1 unit increase in x. It's basically, it stands for the slope. It's the slope of the true regression line. So when we do inference with regression, we're looking at slope. Alpha is the y-intercept, the height of the population when x equals 0. So sigma will be the value that determines to extent which x and y deviate from the population line. If it's small, the observed point is close to the line. If it's large, the observed point is far from the line. So here's a couple things you got to remember from chapter 5. First of all, S sub E. We don't really do variability. We're going to do standard deviation. So SE is really the square root of the sum of the square residuals divided by n minus 2. I'm going to give you computer outputs again so you can find this. And we have to know how to interpret it. Sum of the square residuals is given. Remember, there's a missing typo here. X bar and Y bar are always on the regression line. Your average X, your average Y should always go through the line. In R squared, the formula is 1 minus the sum of the square residuals over the sum of squared totals. And you're going to have to know how to interpret these. Now, what's nice is when you get your regression review, all of the interpretations we wrote on there. So you don't necessarily have to remember them. You'll get this tomorrow. Today we'll just do it together. So what the heck am I even doing? So again, you got to pretend like at each x value there's a little mini normal distribution. So if I said x was 4, so we know alpha is 2, beta is 5, S sub E is 1.3. So this is like the true regression line. We'd have like y hat equals 2 plus 5x. But I'm at x equals 4. So like in all of the little mini distributions, I'm at a specific one when x is 4. So if I plug in x equals 4, what's the probability y is greater than 23.2? So I'm going to plug in 4 for x to find my y hat. So 2 plus 5 times 4. So 5 times 4 is 20, so 22. So this is like your mean value. So that's like your mean. This is our standard deviation. So we're going to go back to chapter 7. I want to find, if I'm at this little mini distribution, where the mean is 22, and the standard deviation is 1.3, what's the probability I get a y greater than 23.2? I'm off the screen. So we're at like a little mini distribution. So I'm going to find the probability y is greater than 23.2. So I got to find a z-score. You guys remember z-scores? So I'm going to find the probability z is greater than, I'm going to take 23.2 minus 22, because that's our mean, divided by 1.3. So I want to find a z greater than 0.92. Now you don't have to get your formula sheet out, I'll just do it off of mine. Remember when we're finding probability, if we have a greater than, what do we got to do? 1 minus. So I'm going to do 1 minus. Now I'm going to look up 0.92 in my formula sheet. So it's kind of like a review. 8212. .1788. So if we all went out and did individual lines, and I got a y that was greater than 23.2, the probability of that happening would be 0.1788. So not too off. If x is 5, so now we're at a different little mini distribution. So now we've moved to where x is 5. The middle 95% of the observed y value should be between which two numbers? So I got to find my new mean. My standard deviation is going to stay the same. So I'm going to plug in y hat now equals 2 plus 5 times 5. So 27. So now I'm at a little mini normal distribution where the mean is 27. I'm trying to find the middle 95%. Should be between which two values? So usually we take the mean plus or minus, now 95%, sort of kind of think of a confidence interval. This is going to be a z confidence interval because we know the standard deviation. So 95% should be 1.96 times the standard deviation. Okay, that's what I'm going to end up doing. So I'm going to take my 27, I'm going to add and subtract 1.96 times 1.3. So it's kind of like finding a confidence interval, but because we know the population standard deviation, we don't have to divide by the square root of n, or because we're not taking a sample. So I'm going to do the minus. So 24.452 to 29.548. So that should be, if I should get between those two numbers to be in the middle 95%. Yes?
If they're like the same thing like standard deviation, why does it have like a different sign? Like, why does it have
Because this is the population standard deviation. It's the standard deviation of the regression line.
okay.
So that's why you have E. Yes. Yes. It's weird. It's weird. Good question. Because eventually we're going to get to the, not on here, but we're going to get to Minitab output, and you look at a different spot. Because there's not just one regression line. So there's a bunch of them.
Gotcha.
So it's like all of them together. Good call. Okay, really what you're going to do more is what example 2 is. So a lot of this, like I said, is going to be review. So everybody needs your calculators out. It's kind of nice that we end with chapter 13 in a way because it does get you to go back to chapter 5. So that when we get to AP review, it's like kind of fresh in your brain. So you need to put number of years out of school in list 1. Amount donated in list 2. And then we're basically going to do a lot of stuff from, like I said, chapter 5. So, X is the number of years. You're looking at the financial director of a private college who's interested in the relationship between the amount of money donated per school year by an alumnus and the amount of years the alumnus has been out of school. So, a random sample of 15 donors gave you the following information. So, this is their one sample. So, do you guys remember how to find your least squares regression line from the calculator? It's okay if you don't. Everybody got their numbers in? Go to stat again. Calc this time. Remember, we do linear regression number 8. So stat, calc, number 8. A plus BX. So list 1, list 2. Your frequency list should be blank. You don't want to store the regression equation and just hit calculate. My diagnostics are off. That's fine. So we'll have y hat equals 1.711 plus 2.789 times x. And then remember to define your variables. So x is the number of years out of school, and y hat is the predicted amount of money donated. So it says, how would you interpret beta? It's basically how would you interpret the slope. So here's our slope. So again, it's for every 1 year increase in x, what's happening to y. We predict what's happening to y. So for every 1 year increase in amount of time out of school, we predict an alumnus to donate $2.79 more. And it doesn't necessarily have to be that. Like I wrote in another one, for every 1 year an alumnus is out of school, we predict the amount donated to increase $2.79. What I'm looking for is, are you predicting 1 year increase in x, how much in y? Alpha would be your y-intercept. So that's my y-intercept. So x is 0 would be what? What does that mean? Just out of school? Oh, they just graduated, I guess.
So years after.
So that would be 0 years after. So right when they graduate. You guys don't know this, but when you graduate college, they don't give you a diploma. They give you a piece of paper that says, how can you donate to the school? That's what I got when I graduated college. And they mail you your diploma. They'll do the same thing in high school, except they won't ask you for money. an alumnus who has just graduated, we predict they will donate $1.71. Again, what's happening when X is 0? Now, S sub B's been a minute since we've had to interpret it. And I actually had to look it up the first time I did this. So, if you don't remember it, like I said, when you get your regression review, it's printed on there. You will need to know it for the test. But for now, you can just copy what I'm writing. 32.143 is a typical amount of variability in the vertical distances from the amount donated to the least squares regression line. So remember, this is your average residual. Again, it's printed on the review you're going to get. Just make sure you know it for the test. So if I substitute, so all that was kind of review. If I substitute X in, or 20 in for X, I get a Y hat of 57.492. I want two different interpretations for this number. So the first one that we did a point prediction. Okay, that was kind of what we did in chapter 5. So we predict an alumnus of 20 years to donate $57.49. So that's your point prediction. Your point estimate, you're estimating for the mean. So the average donation of an alumnus of 20 years is $57.49. So like this is based on if you only had one line. This would be based on if you had different samples of different lines all put together. Okay? So question.